Hey there, Gregory Carlson here for the Calculus Building. Let's do an application of the quotient rule and the product rule. So here we go. It says the temperature of a person who is sick. The temperature of a person during an illness is given by this function down below, where capital T is the temperature in degrees Fahrenheit, and little t is the time in hours. So that's a little confusing. We have the big T representing degrees and the little t representing hours. Find the temperature of the patient at 1 hour, and find the rate of change of the temperature at 1 hour. So you can see our function graph over here. The person gets sick, their starting temperature is 98.6 degrees Fahrenheit. They get sick, so their temperature spikes with a fever, and then it looks like it tapers off a bit. So let's find out what their temperature actually is at 1 hour. And that's as easy as just plugging 1 into the starting function. So if I plug in a 1 here, I get 9 times 1 is 9, over 1 squared is 1, and 1 plus 2 is 3. So that fraction is 9 over 3 plus 98.6. So that's going to be their temperature, and 9 divided by 3 is 3. So they're burning up. If we add that on, their temperature at a time of 1 hour is 101.6 degrees Fahrenheit. So that's their temperature. We can see that that would be a point on the graph right here. And if we look, it looks like if we were to take the derivative, it looks like we're on this rising part of the graph. So it looks like their temperature, we're going to get a positive derivative because it looks like their temperature is increasing at that point. So let's go ahead and calculate what that would be by finding the derivative function. So when we take the derivative, we can completely ignore this 98.6 because the derivative of that constant number is just going to be 0. So that's going to go away. And so let's take the derivative of this. We do the quotient rule, which is low d high, and the derivative of the top is just 9, minus high d low. Hopefully you've memorized that by now. The derivative of the bottom is just going to be 2t, because we can ignore the 2, and the derivative of t squared is 2t. So low d high minus high d low, all over low squared. Okay? So there's our derivative function. This function represents the change of this curve at every moment in time, the instantaneous rate of change, I should say. And so if we find out what that is at 1, basically all I need to do is just plug in a 1 every time I see a t. So that's going to be 1 squared is 1, 1 plus 2 is 3, 3 times 9 is 27, minus 9 times 1 is 1, 2 times 1 is 2, so that's going to be 18. Then on the bottom, I have 1 squared is 1, 1 plus 2 is 3, 3 squared is 9. So that's simplified pretty nicely. 27 minus 18 is 9, over 9 is equal to 1. So that means that at that hour, their temperature is increasing at a rate of about 1 degree an hour. So right here you can see the slope of that tangent line is 1, so they're still getting hotter. If we were to try plugging in, say, 1.5 into this derivative function, you can see that that's where we're kind of flattening off. So I'll let you do that on your own, but you should get a value maybe a little closer to 0 because that's when their temperature is leveling off. So look at the difference. When we plug in 1 into the original function, we get their actual temperature. And when we plug in 1 into the derivative function, we get the rate at which their temperature is changing. And so it's increasing at a rate of about 1 an hour. All right, let's do one more example. We have an invasive insect species, has a total population of this function right here, where t is in hours. So this is the total population function. Find and interpret the derivative at t equals 10. So the derivative, so this function right here is the total population of insects, and the derivative of it is going to be the rate at which that population is increasing or decreasing. So let's go ahead and find that derivative. F prime of t is going to equal, and we're going to do the product rule, and remember that the product rule is derivative of first times the second plus the first times the derivative of the second. So in this case, maybe I shouldn't have used f, but this is kind of the f, and this is kind of the g for the purposes of using this right here, which is, don't confuse that with that f. So here we go. It would be the derivative of the first function, which would be 2t, times the second one without doing anything of it. Okay? And then we would add, and now we would just take this first one without doing anything to it, times the derivative of this one, which would be that would be 3t squared minus 18. So you see how finding the derivative is pretty quick. It's just the derivative of the first times the second plus the first times the derivative of the second. So hopefully that makes sense how I was able to calculate all of that. If not, you should review the product rule section. So now that function right there, that derivative function, tells us the instantaneous rate of change of the insect population at every moment in time. So if we plug in 10, we're going to see what that is at 10 hours. So that would be 20 times 10 times 10 times 10 is 1,000. So that would be 1,000 minus 180, 18 times 10. So that would be 820 plus 10 squared is 100, so that would be 106. That would be 10 times 10, that would be 300 minus 18. And that would be 282. So if we crunch that out, we'll get our answer. So let's do 20 times 820, which is 16,400 plus 106 times 282, which is 29892. And so if we add that to 16,400, we get 46292. So maybe that's not super realistic. I guess it is. No, it's probably not super realistic. Maybe this should have been cells dividing or something, like a virus growing or something. But essentially, if we have this being the total population, if I plugged in 10 right here, that would be the amount of members of the population, the amount of insects or the amount of virus cells or whatever, virus virons. And so the derivative at 10 would be, this is the rate of change per hour. So we plug in 10 to find the total number at 10 hours, and we plug 10 into the derivative function to find the rate of change at that 10-hour mark. Hopefully these applications make sense to you. If you have any questions, please leave them in the comments. If this video was helpful, please make sure you like and subscribe and share it with your friends. And I will see you in the next section at the next level of the calculus building. See you there.